What's up, everyone? How are you all doing today? Today we are starting a new topic, right triangles. And for this lesson, it'd be helpful to have a couple of crayons, markers, colored pencils, some notebook paper to take notes on, and a pencil. And like with the last couple of videos, what I'm trying to do is put red stars next to these slides that you should be taking notes on. And then if you were taking them Cornell note style, you want to just make sure that you have the unit, the topic, the questions, and the main ideas on one side, and then the bulk of the notes on the other side. And then I always like to have the name and the date as well. So if you can do Cornell note style, that's great. If you have your own style of taking notes, that's cool too, just as long as you're taking notes throughout the video. So try and pause the video right now, gather all the materials, and once you're all set, let's begin. So some topics we'll be covering are the Pythagorean theorem, special right triangles, right and oblique triangle trigonometry. So we'll be getting these first two bullet points this week, and this last one we'll be learning more about next week. So don't worry if by the end of this week you're still kind of confused on this. We'll get more to that next week. So as we explore this unit, these are just some good questions you want to have in the back of your mind as we move forward. What are the various tools I can use when I'm working with right triangles? Where do I see right triangles in everyday life? So our first topic, we're just going to be simplifying radical expressions using the Pythagorean theorem and its converse to solve problems and solve word problems involving right triangles. So this lesson, we'll probably just get to this first bullet point today. So hopefully after this video, you'll be very comfortable with simplifying radical expressions. So first, some kind of prerequisite knowledge you need to move forward is how to combine like terms. A lot of you may already be comfortable with this. If you are, you can go ahead and kind of go over these quickly. But if not, I'm going to go over these a little bit more in depth and slowly so you can follow along. Or you can fast forward and kind of check your answers once you're done. So the way I like to think of this, 2x, 10x, and 11x, those are all like terms because they all share the variable x, and that's x to the first power. So 2x, 10x, and 11x, those are all like terms. So 2 minus 10, that's negative 8. Negative 8 plus 11 is 3. And then we just carry the x. Now let's see, we have 5x plus 5y, so those are not like terms, plus 5, which is just an integer. So because those are not like terms, none of those are, we can't simplify that any further. So that's just going to be 5x plus 5y plus 5. Let's see, we have 2x squared plus negative 5x squared. Okay. Minus 6x. So 2x squared and 5x squared, those are like terms because they share the variable x and it's to the second power. 6x is not a like term with those because the exponent with this x is just to the first power. So doing the ones in blue, 2x squared minus 5x squared, or plus negative 5x squared, that's going to be negative 3x squared. And then we can't really simplify negative 6x anymore, so we're just going to carry that on. All right, we have 3x times 4x. Well, 3 and 4, those are integers, so we're going to multiply those together. Whereas x and x, those are the same variables, so we're just going to multiply those. So 3 times 4 is going to give us 12. X times x is going to equal x squared. All right, so we have root 5 minus 2 root 5 plus 5 root 5. All of those are like terms because they share the radical root 5. Likewise, if this was just x minus 2x plus 5x, kind of like in the first one, we would just add the coefficients and then carry on the variable. So root 5, we can think of that kind of as 1 times the square root of 5. So if we have 1 root 5 minus 2 root 5, well, that's going to be negative 1 root 5 plus 5 root 5 is just going to give us 4 root 5. See how 1 minus 2 plus 5 is going to be 4. and then we just carry the variable root 5 over. And then if we were to multiply these, we could multiply 3 and 4 because those are integers, and then root 6 times root 7 because those are both radicals. We will multiply those. So 3 times 4 is 12. Root 6 times root 7, so times root 6 times root 7 is going to give us 12 times root 42. So simplifying radicals, again, so when radicals are in their simplest form, we will not have a perfect square factors under the radical sign. We will have no fractions under the radical sign, and we'll have no radicals in the denominator. So some examples of what those might look like. These are not in their simplest form. As we can see, the square root of 12 over 4, well, that's a fraction under the radical sign. Root 4 over root 2, we have a radical in the denominator. And root 4, well, 4 is a perfect square under the radical sign, so we can simplify that further. This we have a radical, and then with these last two, we have radicals in the denominator. So these are not examples of radicals in their simplest form. So how do we rationalize the denominator? Well, what does that mean? That is the process of eliminating radicals or imaginary numbers from the denominator of an algebraic fraction. That is to remove the radicals and a fraction so that the denominator only contains a rational number. So we'll kind of explore what that means. So how to simplify a radical. So let's say we were going to write the square root of 27 in its simplest form. First, we're going to ask ourselves, does the number under the radical sign have any perfect square factors? Well, yes, because 27 is equal to 9 times 3. 9 is a perfect square factor. So we're going to rewrite the expression. So square root of 27 equals square root of 9 times the square root of 3. And because the 9 is a perfect square, we can simplify that to just 3. So we have 3 root 3. And then, since the square root of 3 has no perfect square factors, so you are done. 3 root 3 is in simplest radical form. So let's go over some examples of rationalizing the denominator. So let's say we have 4 over the square root of 6. So we have a radical in the denominator, and the way we can get rid of that is essentially we're just going to multiply this fraction by 1, because if you take any number and multiply it by 1, then the value of the number does not change. But the way we can multiply this 1 so that the form changes and we no longer have a radical in the denominator is if we multiply it by root 6 over root 6. See how root 6 divided by root 6? That's just 1. So 4 over root 6 times root 6 over root 6, that's not going to change the value of this, but it'll change what it looks like. 4 times root 6 will give us 4 times square root of 6 over, well, root 6 times root 6 is going to be square root of 36. And then we can simplify that even further, so it's 4 square root of 6 over 6. Likewise, with 10 over the square root of 3, we want to multiply that by 1 so that we're not changing the value of our answer. So 10 times the square root of 3 is just going to be 10 root 3. Root 3 times root 3 is going to be root 9. And as we know, the square root of 9 is just 3. Now we have the square root of 12 over 4. We can actually rewrite that. So it is the square root of 12 over the square root of 4. Well, the square root of 12, we can simplify that. So that is the square root of 4 times 3. And we know the square root of 4, that's just going to be 2. So I'm going to bring this down here. Square root of 4 times the square root of 3 over 2. And we know the square root of 4 is 2. So 2 times root 3 over 2. And for our last step, we can just cancel out b2's and we get the square root of 3. Now, see if you can pause the video and try these out on your own. And if you're having trouble, I'm also going to be going over them as well, so no worries if you are. So 2 times the square root of 27. How can we simplify that further? Well, is there a perfect square that goes into 27? There is. 9 goes into 27. 9 is a factor of 27, so we can rewrite this as 2 times the square root of 9 times 3. Because 9 times 3 is 27, so that's going to equal 2 times the square root of 9 times the square root of 3. Well, the square root of 9, we know that to be 3. So 2 times 3 times root 3. And then 2 times 3, that's just going to give us 6. 6 over root 3. And that is in simplest radical form. So let's try another one. And again, we want to make sure our answers are in simplest radical form. So 6 root 5 times 4 root 5. So I'm just going to get my marker. We can do 6 times 4 because those are integers. And we can multiply root 5 by root 5 because those are radicals. Well, 6 times 4, that's going to give us 24. Root 5 times root 5, that's just going to be the square root of 25. So that's going to be 24 times 5, because the square root of 25 is 5. And that's just going to give us 120. All right, third example, 3 root 6 plus 4 root 54 minus the square root of 6. Well, with this problem, you might be thinking, oh, the square root of 54, that's not a like term with root 6 and root 6. But we can actually simplify this even further. So if we were to simplify this, we can make this 3 square root of 6 plus 4 times the square root of, well, 54, that's just going to be 6 times 9. Times 6 times 9 minus the square root of 6. So that's just going to give us 3 root 6 plus 4 times the square root of 6 times the square root of 9 minus the square root of 6. So we can have 3 root 6 plus 4 times the square root of 6. Well, square root of 9 is just going to be 3. So plus 4 times 3 times the square root of 6 minus the square root of 6. So then we can simplify this even further. So 4 times 3 is just going to be 12. So 3 square root of 6 plus 12 square root of 6 minus square root of 6. 3 plus 12 minus 1, because again, we can just think of this as 1 times the square root of 6. So 3 plus 12 is 15, minus 1 is 14. Square root of 6. All right, example 4. We have the square root of, square root of 6 over 25. Well, that's just going to be square root of 6 over the square root of 25. And that's just going to be equal to the square root of 6, because we can't break that down any further, over, well, square root of 25 is 5. And that's in simplest form, because we have a radical in the numerator, but not the denominator. So that's okay. And for the last example, we have 10 over the square root of 3. Again, we just want to multiply this by 1, so we're not changing the value. So the way we're going to get rid of the radical in the denominator is just multiply it by itself. So we get 10 square root of 3 over, well, root 3 times root 3 is just going to be root 9, and the square root of 9 is 3. And that's in simplest form.